This is the third webinar of the European project CiROCCO. The webinar deals with data synergies when it comes to atmospheric desert dust. So as we all know, dust is frequently uplifted from the African desert areas, flowing towards the Mediterranean or the whole Europe through several identified pathways. And the forecasts of air production loads and wind flows and the duration of such events depend on multiple soil and atmospheric parameters. Thus, the exploitation of any relevant measurements can import huge improvements in numerical modeling efforts. So, having a quick view at the agenda, first our project manager, Chrysoula Papathanasiou, will explain what CiROCCO is. And then two researchers, as well from the National Observatory of Athens, will elaborate both on numerical modeling and remote sensing of the atmosphere linked to dust aerosol.
Okay, starting with a few facts and figures for the project. The vision of our project is to establish an integrated sensing system. It will be composed of a network of low-cost and high-end sensing nodes, distributed network of these nodes. The data from these sensors will be coupled with state-of-the-art data fusion, remote sensing, and assimilation modeling techniques. What we aim to do eventually with this monitoring network of sensors is the enhancement of the current lack of ground observation in desert areas, undersampled areas, offering an operational at the same time an easy to maintain and expand solution. So for this project, we have 12 partners joining forces from 7 different countries. You can see the geographic distribution here. As I said before, ICCS is the project coordinator, and we have a diverse group of partners from different countries again, and different domains. We have 5 academic and RTOs. Apart from ourselves, we have NOAA, CEDARE from Egypt, University of Cyprus, and CICIC from Spain. We have 3 SMEs, EBOS from Cyprus, Astro from Switzerland, and Innocence from Serbia. 1 industrial partner, Intra, net company currently named from Greece. 3 public organizations, a municipality in Cyprus, Ministry of Labor again in Cyprus, and Visium in Serbia. Now, which are the main objectives of our project? We have different range of objectives, starting from business objective, installation and operation of in situ, low-cost, standalone electronic sensing nodes, and ensuring that we attract the interest from local communities, which is one of our goals. In terms of technical objectives, the first one is the establishment of low-cost and sustainable network of these electronic sensing nodes that will monitor undersampled desert areas and ecosystems in Egypt, Serbia, and Spain, and also monitor conditions in Cyprus. And the development of data processing services that are based upon ICT infrastructure, gaining data sets from hard-to-reach undersampled areas, and improving the quality of the data sets by using data fusion services. We have also 2 scientific and innovation objectives. The first one having to do with our aim to enhance climate change models with the data and further support the research for the European Green Deal challenges. And the second one has to do with the integration of our data in the cross-Copernicus ecosystem and assimilation services. And we have a final impact maximization objective that has to do with the acceleration of the adoption of our CiROCCO solutions, tools and services, the adoption by the wider community, so as to ensure that we maximize our impact. Now, in this figure, you can see the concept of CiROCCO. So, as I said before, there is a mix of low and high-end cost high-end sensors. We foresee data fusion services between high and low-end sensors. We also foresee data fusion between Earth observation and in situ measurements. In terms of communication, we have wireless and satellite communication that will support this data collection. And all these data sets will serve the needs of 4 different pilots: air quality, early warning system for human health, renewable energy systems planning, land use and ecosystem management, and modeling of greenhouse gases and particles emission. And on top of these services, we target EU, the sharing at EU level of data sets and services and the development of business models. In terms of outcomes, in brief, apart from the installation of our sensors in 3 desert regions that will be fully operational for at least 10 months, datasets will be made available to the community. They will cover an area that expands over 2,000 square kilometers with 69 stations in total, monitoring 10 parameters for these 10 months. The low-cost sensing system will be made available at a price by 60% lower than the price in the current market. The validation of the datasets will come through their application in our 4 pilots mentioned before, and we also aim to offer increased accuracy in the developed models and maps and improvement by 10% with using our in-situ datasets. And of course, we target collaboration with at least 5 working groups of GEO, Copernicus, and ESA, promoting our in-situ component. And here you can see the geographic distribution of our 4 pilots. The first one, renewable energy systems planning, the pilot is in Egypt and more specifically at the Benban Solar Park. The second one, desert dust storm events monitoring, is our pilot in Cyprus. The third one, sustainable environmental restoration support, is our Serbian pilot, and the pilot area is Delibliato Sands in Serbia. And the fourth pilot is modeling of greenhouse gases and particles emission, focusing on our pilot our pilot area in the Tabernas Desert in Spain. That was all. In a nutshell, I said before. Thank you very much, and back to Eleni for monitoring discussion.
Yes. Eleni's PhD is on dust modeling. And as I said, she's a researcher at the National Observatory of Athens, and she contributes to CiROCCO with her expertise. So let's see all the progress that she has made.
I'm Eleni Drakaki. I'm a PhD candidate at National Observatory of Athens. Today I will presenting on the topic understanding and improving dust forecasting through satellite synergies, the CiROCCO perspective. In this talk, I will walk you through the key challenges in dust forecasting, how models and observations can work together, and how CiROCCO project is developing new approaches to improve dust predictions, combining models and observations. Let's begin with why dust really matters. Here are some real-world events that highlight the importance of accurate dust forecasting. In June 2020, the so-called Godzilla dust cloud crossed the Atlantic Ocean, increasing PM10 concentrations in Puerto Rico and reducing the air quality below the health standards at 40% of the United States air quality stations. Here in Greece, another example is the Minoan Red event in March 2018, when air quality and visibility reduced in Crete mostly. More recently, some days ago, a dust event in Delhi airport caused delays on more than 200 flights, and 50 flights were diverted to another airport. And also, we are aware about the climate change and the increasing temperatures and the role of aerosols and specifically dust on that. So dust is not just an atmospheric irritant. It has more far far-reaching impacts on climate, on health, on aviation, on weather, and on ecosystems, and in general on economy. On climate, dust alters Earth radiative balance through scattering and absorbing radiation. On health, fine dust particles reduce air quality and cause respiratory problems. On aviation, dust reduces visibility and cause delays and flight diversions. Regarding weather, dust interacts with clouds, alters cloud formation and precipitation patterns, while on ecosystem, dust has a dual role. On the one hand, delivers nutrients like iron and phosphorus, while on the other hand, can cover vegetation, causing agricultural problems. All these impacts have extensions on economy, and this is why the dust forecast and monitoring should be both a scientific and societal priority. But let's start from the basics. How dust enters the atmosphere, how it is transported, and how finally deposited to the ground. This process includes 4 key stages. Emissions is when strong winds blow over dry soils, lift dust particles, and dust particles enter into the atmosphere. Transport, as dust particles have entered into the atmosphere, they can travel thousands of kilometers due to the atmospheric circulation. The interactions of dust particles, when dust particles are within the atmosphere, they interact with both short-wave and long-wave radiation, both cooling and warming atmosphere, and also interact with clouds. Dust particles are effective cloud condensation nuclei and ice nuclei, which means that dust particles, because of their shape and their composition, attract humidity and help forming cloud droplets and ice crystals around them more easily rather than if no dust particles were there. And finally, the deposition process, which is the removal process of dust particles from the atmosphere. Deposition has 2 kinds, dry and wet deposition. Dry deposition is the process where dust particles eventually settle to the ground due to gravitational forces. And wet deposition is the rain washout, when dust particles below clouds are removed from the rain droplets. Dust particles vary widely in size in the atmosphere, from less than 0. microns to over 100 microns, and these are the categories, the main categories that we divide dust particles depending on their size and also their effects on the Earth system. But now that we have understand the dust life cycle, let's take a look on the tools that we have to simulate the dust life cycle, which are the atmospheric dust models. There are many of them designed for different purposes. Here are some of the most widely used. Some of them are designed for short-term forecasting. Some are designed for long-term dust climate interactions. In terms of design, models differ on how they simulate dust processes. Some models are online coupled, which means that dust emissions, transport, and meteorology interact in real time within the model, while others are offline, where meteorological data is fed in a separate dust module. And these different coupling strategies can have an impact on how responsive can be a model to rapidly changing conditions like a sudden dust outbreak. Dust models also vary in their geographic scope. Some of them focus on regional forecasting, providing detailed local insights, while others are global, covering the entire Earth but at lower resolutions. Choosing the right model depends on the question being asked, whether it is forecasting a dust storm for tomorrow or understanding the climate interactions over the decades. Observational data also is essential for improving model performance. Data assimilation is a process that allows models to ingest real-world measurements like aerosol optical depth or better dust distributions. And without observational input, models may miss key features, especially in regions with complex terrain and sparse monitoring. We will come back to that idea when we will discuss specifically for the CiROCCO approach. Rather than relying on only one model, many operational centers compare outputs from several models. This is the so-called ensemble approach, which helps to manage uncertainty and make forecasts more robust. A good example of this is the Barcelona Dust Regional Center, which integrates results from several models. Let's now explore the challenges in dust forecasting. This slide highlights how different models produce very different total dust loads in the dust burdens in the atmosphere. These are the results from the AeroCom3 intercomparison study, which compares multiple global models, dust models. And we can see that the simulated dust burden across these models differ up to 31%. This difference stems from uncertainties in both emission processes and dust life cycle. And these differences are caused because we face several challenges in dust forecasting. Firstly, dust originates in vast desert regions that are poorly monitored. These areas often lack ground-based instruments like weather stations or sun photometers. As a result, we rely heavily on satellites to observe emissions and dust plumes. But satellite data have limitations. So they doesn't tell us all the truth, and especially what is happening near the surface. Sparse monitoring reduces the accuracy of both emission estimates and early warning systems. Another key challenge lies in the parameter uncertainties. Dust emissions depend on mainly soil-related parameters like moisture content, roughness, texture. These parameters are often poorly known and generalized and simplified in models. Different models use different parameterizations and leading to big differences in the simulated emission fluxes. Here is an example of the simulated emission fluxes under different parameters, and we can see how different can be the simulated fluxes. So even with the same meteorological input, two models might produce very different results. Sorry. Even as I said, meteorology also plays a very important role in the simulation of emission. Here is an example of simulations driven with different meteorological initial conditions. From different datasets, GFS and ERA5, we can see that using different meteorological conditions, we can have almost double emission fluxes, double simulated emission fluxes. Another important factor is topography and the meteorological conditions around topography. Dust emissions are highly sensitive to wind speed, surface turbulence, and atmospheric stability. Small errors in these fields can lead to large errors in dust output. For example, incorrect wind forecasts can cause model to entirely miss an emission event or misplace the dust plume. Here is an example of in the left-hand picture we can see where that the emission hotspots are where the wind is stronger, and on the right-hand figure we can see how a cyclonic circulation can drive the emission and the transport of a dust plume. Dust emissions and transport are also strongly influenced by topography, as I said, and here in that slide we can see how the model resolution is related to the topography. We can see results from simulations using different resolutions and simulating details of topography differently. As we have higher resolutions, we have more detailed topography in the model, and this can lead to major differences because due to topography, topography can funnel winds and generate dust concentration hotspots that are not simulated when we use coarse model resolution. Another significant modeling challenge is accurately representing the size distribution and the lifetime of dust particles. Models tend to struggle simulating coarse particles, those especially that are larger than 5 microns in diameter, as we can see here. We can see here that in this study we find that we need almost 8% reduction of gravitational forces in order to counteract the missing processes in the model and fit the model results with observations. This highlights that models may miss some major mechanisms in the parameterization of dust life cycle, such as turbulence or convective mixing, and this can lead to lower simulated burden in dust burden, lower simulated dust burdens, and also underestimation of the radiative effects of dust. Now let's move to observation, specifically how we use different satellite instruments to improve dust forecasting. Here are some examples of satellite instruments. MODIS, for example, gives us high-resolution horizontal information, and EOD, aerosol optical depth maps. SEVIRI is a geostationary satellite providing rapid temporal updates, but with limited geographical cover. While Calypso adds in the information providing vertical profiles of dust and aerosols in general, helping with identifying dust layering. Each sensor contributes to the puzzle And when we combine them, we get as much more complete view of the atmosphere as is possible. Here we distinguish the difference between 2D and 3D satellites. Here is an example of MODIS aerosol optical depth map. It's a 2D simulation, it's a 2D information because aerosol optical depth is a columnar product. And here is the severe imagery also, a 2D information product. And here on the right is a Calliope profile that provides the vertical distribution of aerosols. Manolis later will explain us more about the differences of the products and the benefits that we can take from the Calypso vertical distributions. This slide here emphasizes a key point that no single satellite provides all the answers. By combining the different instruments, we can have a better insight, and we can have the whole picture, as we can see, if we can say. While satellite data is essential, it's only part of the picture. We also rely on ground-based and aircraft observation for validation, but also for deeper insights. Ground-based stations give us continuous high-quality data at specific locations, including PM concentrations, aerosol optical depth, and vertical profiles of aerosols. Aircraft campaigns, on the other hand, offer targeted in situ measurements within dust plumes and are especially valuable for capturing vertical structure and size distribution. Together, all these platforms can help us evaluate and calibrate models, but also satellite retrievals. Sun photometers is an instrument that provides aerosol optical depth measurements. Here is an example of the Simel photometer at Pangea Station in Antikythera. And on the left hand is a figure with the Aeronet stations. We can see here that above the arid regions, we have a lot of sparse monitoring. And here is an example of the kind of information that we can take from such a station. We can take time series of aerosol optical depth, and we can compare it with time series from models. Another option of low-cost sun photometers is the Microtops and the Cali2 instruments. In CiROCCO's perspective, we have applied such an approach. And also we have ground-based measurements, as I said previously, that provide particulate matter concentrations. There are some more sophisticated instruments here on the left, and some other lower cost solutions, and they can provide time series of particulate matter concentrations near surface. Another type of ground-based measurements is the LiDAR measurements, which provide vertical profiles of aerosols. And another component also is the aircraft measurements. When specific instruments that measure particle distributions are mounted on aircrafts and allowing in that way taking measurements within clouds or within dust plumes and providing information about the dust size distribution. Here is an example of a LiDAR profile in this case, because also LiDARs can be mounted on aircrafts, which provides a profile of aerosol dust, of aerosol backscatter. These observations can help in the model performance assessment. Here is an example where we have 2D aerosol optical depth from satellites and 2D model aerosol optical depth against observations and against also satellite profiles. Here is also an example where we compare dust size distribution from the model and from aircraft measurements. And here is another way that we can use observation in the models through data simulation. We can ingest satellite data into the model, and in that way constrain the model forecast towards observation. Following the same perspective, let's now focus on the CiROCCO project and its unique contribution. The main goal is to merge in situ and Earth observations data to improve dust modeling, and CiROCCO aims to enhance dust simulations and air quality and environmental impact studies. In CiROCCO, we are using the WRF-Chem model, and we are using satellite data from MIDAS dataset. We assimilate MIDAS dataset into the model, providing two different datasets, the initial forecast of the model and the assimilated simulated dust fields, which is called analysis. All these data are stored in the CiROCCO stream handler, which is a database, and makes this data available. The atmospheric model that we use, the WRF-Chem, has 12-kilometer resolution and provides 3 hours model output. The resolution is sufficient for simulating mesoscale meteorology and dust transport. We use the Gokart dust emission scheme, GFS initial and boundary condition, and we have the RRTMG radiative scheme for cloud radiative interactions, and the LIN scheme for macrophysics interactions. We deployed, as I said previously, MIDAS dataset. MIDAS dataset is a 2D product, dust optical depth, specifically provides information about dust and results from a combination of the MODIS Aqua level 2 aerosol optical depth and collocated MERA2 DOD to EOD ratio. We apply a Newtonian relaxation method to assimilate MIDAS into the model. And we have select a 12 hours time window for the assimilation, which is a decision based on the satellite orbits in order to have enough data for the assimilation. And here are some first results where we can see that how the initial forecast here on the left is improved using the MIDAS dataset. Here is another example, also for another date, and we can see here also the results against the MSG dust RGB product, and we can see how the model missed entirely this plume initially, but after the assimilation captures the dust plume. Also, another example here against the VIRS. We can see here that the intensity of the simulated dust plume is improved here after the assimilation. But also this method has some limitations. The assimilation of aerosol optical depth, because it's a columnar product, provides only information about the horizontal distribution of dust and do not offer any information for the vertical distribution of dust. And that's why in the future synergistic approaches are needed. Here are the plan for the CiROCCO project is to apply this methodology during the CiROCCO campaign in summer 2025 and compare the model outputs against the collected measurements, the collected surface PM2.5 and PM10 and AOD measurements from the 4 pilot areas, Spain, Serbia, Cyprus and Egypt. Some future directions and some challenges for dust modeling include more intense efforts for columnar products that provide information about the vertical structure of dust. Machine learning algorithms are very promising for short-term and now for short-term forecasts and now casting, and also the upcoming missions of EarthCare and Aeolus #2 will improve our knowledge for the meteorological conditions, the aerosol distribution, but also help us in the validation and data assimilation in the models. That was from my side. Thank you very much for your attention.
So please, you can, if you think of any questions, please put them in the chat or note them down so that you take the questions after Manolis, who is a researcher for many years now at NOAA, and he will discuss right now on the remote sensing of dust.
Well, thank you all for being here. Eleni Drakaki presented very nicely a broad overview of atmospheric modeling and forecasting of dust, of atmospheric dust. The objective of this presentation here is to briefly provide some insight on the support of Earth observation and Earth observation-based products of dust to this atmospheric modeling efforts, and in total, how this could provide some support to services towards the citizens as it happens through the CiROCCO project. So, as Eleni Drakaki summarized very nicely, there are some challenges related to modeling the full cycle, atmospheric cycle of dust from emission to transport and eventually deposition, related, for example, to the lack of information to support the validation and evaluation activities of models, to support and quantify the forecasting in terms of whether or not it is accurate or not. This information is quite dependent on having the full four-dimensional insight on dust in the atmosphere, meaning spatial and temporal evolution of dust. Having information regarding the activation regions, arid, semi-arid, hyper-arid areas, and eventually to manage to quantify also the end of this life cycle of dust in the atmosphere, relate the position and the support towards the ecosystems. As Eleni said, dust is related with minerals deposited. And of course, data assimilation and machine learning techniques are also dependent on the amount of data that can be provided to these activities. In the framework of the CiROCCO project, till this moment, the MIDAS data record has been extensively utilized, and more specifically, the dust optical depth. Let's take a step back here. What is the dust optical depth for those that may not be familiar with? Assuming that the radiation is propagated in the atmosphere and it interacts with molecules and particles. Some of this radiation is backscattered, some is scattered to other directions, some is absorbed. This is actually the extinction, how much of this radiation is extinct in the atmosphere. Having the vertical integration of this property of the extinction, the integration with respect to height and of only the dust component and not of the other aerosol, is the dust optical depth. Just to have a metric on this, Athens during this season of the year, the June, July, August, is characterized by a mean dust optical depth of approximately 0.15 and an AOD approximately of 0.3. This information of the dust optical depth has been used in CiROCCO. This information is highly dependent on many parameters. For example, depend on the mineralogy of dust particles, on the particle size distribution, or on the elevation of the atmospheric dust, the layer in the atmosphere. For example, let's have an example here. Let's assume that we have three different layers of dust. One is detached in the surface of the Earth. One is just above the planetary boundary layer, and the other one, the third one, is transported in the free troposphere in higher altitude. The first one will impact air quality. The second one will provide dust particles that will act as cloud condensation clay, while the third one, being higher in the troposphere, will act better as ice nuclide particle. That means that although having in MIDAS the dust optical depth, this integration with respect to height will provide exactly the same dust optical depth, though these three layers will have different impact on air quality, on climate, will be deposited, removed from the atmosphere different or faster or slower. To address this issue, there are two different types of sensors when it comes to Earth observations of aerosols, to satellite-based Earth observation of aerosols, the passive and active sensors. The MIDAS dataset that has been used till this point is based on MODIS observation above Aqua and Terra satellites, and it is which are passive sensors. That means that they do not have their own source of light. They use the sunlight, the radiation from the sun, the solar radiation, and the backscatter, the thermal radiation emitted from the Earth's surface, and provide information on the UV, visible, and infrared spectrum. On the contrary, active sensors, just like Calliope that Eleni mentioned before, has its own, it's a LiDAR system. It emits its own light pulses. These light pulses propagate in the atmosphere, interact with aerosols, scattered towards different directions. Some of its light, it's backscattered, collected by the sensor, and provide information on the vertical structure of dust in the atmosphere. That does mean these dust products, depending on these different satellite sensors, may provide different information complementary, just like the two sides of a coin. However, it is important that all the products are validated and cross-compared before use. So that doesn't mean that the MIDAS product that has been used till this point has some deficiencies. It just can't provide the four-dimensional structure of aerosols in the atmosphere. Let's have a look now on what the four-dimensional structure could provide. Calliope and EarthCare that Eleni mentioned emit Calliope is the LiDAR system on board Calypso, which is used here for these figures. EarthCare is an ongoing satellite that has athlete and needs a different LiDAR on board. Both of them have the capacity to provide the depolarization property of aerosol particles. What does it mean? Well, both Calliope and Athlete emit linear polarized light. These pulses propagate in the atmosphere, interact with aerosols, and and a portion of this light is backscattered. Now, dust particles, due to their non-spherical shape, have the capacity to depolarize the polarization state of light. What does it mean? That the linear polarized light, when it returns to the sensor, back to the satellite platform, it returns with a different polarization, which is measured. So having this information, which is something like a fingerprint, like a signature of dust in the atmosphere, we may have information not only on we may have information of the subtype of aerosol in the atmosphere. This is shown here on the two figures. On the left figure, you may see the vertical structure of the atmosphere. It is in a region to the west of the Saharan Desert, where we may see a dust layer in the atmosphere. And also you may see the depolarized, the particulate depolarization ratio, which is between 0.2 and 0.3, which means that it is dust. It is classified as dust. Having this information, we may process all these overpasses over each region and decouple the dust component from the non-dust component, and eventually have a climatological information of what dust on the amount of dust over an area. This is shown here on the lower right figure, where we have decoupled the total aerosol, which is the blue and the orange color, the profile, from the dust component, the pure dust component, which is shown with the orange color. This is the extinction. Having the vertical integration, the integration of the total extinction and the dust extinction with respect to Hive, we have the total AOD, which is the lower upper figure, with the dust optical depth, which is the lower right figure. Now, some applications which provide support, which provides the information how these products can be used, provide support towards services to the citizens. Starting from evaluation, validation of models, just like in the CiROCCO project, where we can see that this product has been used to validate the DREAM model, the MAC, and also some intercomparison against MERA. And some other information that this product can provide is related to air quality. For instance, here you may see some cross sections of the dust of the coarse mode and the fine mode component. The larger the particles, the less severe the risk toward the human health is. Over the New Delhi region, where we may see that this area is characterized by mass concentration of dust that may be climatological, even 25 higher than the World Health Organization limits. Just like as used in the CiROCCO project, we may have information on through having information on the extinction coefficient profile over an area, we may have information on how much of this radiation is lost, which is useful for solar plant villages. This is an example of the profile of dust over a solar plant village over in the Morocco area. And finally, another application which is very interesting, I think that it's very interesting, it's related to an accident, the Air France 447 accident a few years ago. This study published in Nature a few years back, where the authors ran a model. You may see the area where the accident happened. And they found out that during the accident, there were some very strong updrafts and downdrafts of air, most probably related also to IN from dust particles releasing latent heat and invigorating this thunderstorm, which is quite probably that led to this accident. So this is from my side. Thank you very much for your attention.